So how we've been using matrices, we've just been using the matrix to store, well, an augmented matrix actually. Um, and yeah, I don't know. I don't really care about the distinction between a matrix and an augmented matrix. But all we've been using them for is to store the coefficients of our system of equations. Matrices actually have their own arithmetic involved. And just a quick reminder, when we're talking about a matrix, the size of the matrix is the number of rows by the number of columns. So the size of this matrix right here, it has 1, 2, 3 rows and 2 columns. This is a 3 by 2 matrix. When we're talking about a square matrix, that is, the number of rows matches the number of columns. So this would not be a square matrix if it was just, say, the first 2 rows, 1, 2, 3, 4, like that. That would be considered, or that would be a square matrix. This is a 2 by 2. All right. So in order to be able to add, that's just a quick definition. In order to be able to add 2 matrices, what has to happen is the dimensions have to match. Of the 2 matrices we're talking about. So in this instance right here, you can see we have a 3 by 2 matrix and another 3 by 2 matrix. This one's 3 by 2, this one's 3 by 2. They're both the same dimensions. They're both 3 by 2, which means they can be added. And when we do that, and when we add them together, how we're going to do that rather is we're just going to do it entry-wise. We're going to look at the kind of the first row, first column, add it to the first row, first column, and that gives us the first row, first column. And we're going to end up with a 3 by 2 matrix as well. And everything is going to, this is just 6 different independent addition problems. 2 plus 1 is 3. 3 plus 3 is 6. 4 plus 3 is 7. 5 plus negative 2 is 3. And 6 plus 7 is 13. Pretty straightforward addition. And subtraction works the same way, but when we're doing that, if we were to do this, do a 2 by 2 matrix here, we do 1 minus negative 1, and that can be a little tricky. So one thing that can be handy to do here is to take this negativity, this negative that's on the outside of this matrix here, that's subtracting this matrix, and kind of distribute that through here. So you might want to do it like this. You might want to say, okay, 1, 4, negative 3, 2, and that's just the first matrix there, and change this to addition instead of subtraction. And in doing so, we're just going to change the sign of each of the numbers in this matrix. So 1, negative 3, 2, negative 4. Then we just have an addition problem, which is a decent amount easier to deal with. 1 plus 1 is 1, or 2. 1 plus 1 is not 1. 1 plus 1 is 2. Here we get a 1. Here we get a negative 1. And here we get a negative 6. That's pretty straightforward also, with the one addendum of having to deal with the negativity there. And this actually, you can see this actually can be split up. One matrix equation like this can actually represent 4 separate individual equations, because if this matrix plus this matrix is equal to that one, in order for that to be true, then, well, this entry plus that entry has to be equal to this entry. So 2x plus 1 plus negative 1 must be equal to 4. And, and then 3 other equations. Let me go ahead and solve this one, since this looks like an equation I can solve. 2x plus 1 minus 1 equals 4. So the parentheses weren't doing anything. Those two things cancel each other out. We get 2x equals 4. Thus x equals 2 when I divide both sides of this equation by 2. So that tells me x equals 2. If I wanted to look at this entry, 1 plus 0 equals y. That one's pretty easy to solve. It's already solved. 3x plus 0 equals w. Uh, 3x plus 0 equals w. We already know that x is equal to 2. That had to be the case from up here. So this is 3 times 2, which is 6. So we get w equals 6. And lastly, z minus 2 plus 2 equals negative 5. Those parentheses aren't doing anything, so I can just drop them. Z minus 2 plus 2 equals negative 5, and they just cancel. So we got Z equals negative 5. And so you can see I found the values of those 4 variables.